Hello everyone, today we are going to be learning about the binary search algorithm. We'll start off by understanding what the search for problem is. We'll try to look at a naive search algorithm and then we will move on to understanding what exactly the binary search algorithm is. So let's understand what the search problem is. In computer science, the search problem is basically defined as that given a collection of data and a specific input, you have to figure out whether that specific input exists in that collection or not. If it exists in the collection, you return true. If it does not, you return false. So to make it more formal, let's say, for example, you're given an array of numbers. In our case, let's say we have 7 elements in the array. 12, 15, 19, 20, 25, 32, and 38. Yeah. You're given a specific input, which we call key. Let's say our key is 32 here. Your goal is to find if key exists in the array. So let's look at a naive way of doing it. So what we do is we basically start looking into the array. We start off with the first element, which is 12. We compare it to the key, and whether the first element is equal to the key or not. If it is, then we return true. We have found the key, we return true. If it does not, we move on to the next element. So start off with 0 at the index 0. If 32 is not equal to 12, so we move ahead. It's still not equal. We keep moving ahead until we hit the point where it matches the key. So this was a good case where the key was present in the array. If it was not, then you will eventually reach the end of the key without finding the element, and you can return false, stating that the key does not exist in the array. Okay. So in this particular case, it took us 6 steps to determine if the key existed or not. If the key exists. Okay. So now let's look at a more general time complexity. Okay. So what exactly are we doing? We're basically comparing every element of the list with the key. So our time complexity is basically O of n, where n is the number of elements in the array. I might be using the word array and list interchangeably. It's the same. If you're using C++, it's array. It's in Python, it's called a list. So yeah, the time complexity is O of n. Okay. This is pretty decent to a million or a billion records, but as you go further to a trillion or 100 trillion records, this is still pretty slow. So now the binary search algorithm tries to improve upon the time complexity by adding structure to the array. Let's look at the binary search algorithm. I'll remove the rest. I'll keep clearing the key. Yeah. So in the binary search algorithm, we add a structure to the array, which is nothing but sorting. We basically sort all the elements in our array in ascending or descending order. So in this case, it is already sorted in the ascending order. So we will see how this sorting or adding this structure by sorting the array helps improve on the time complexity. So let's look at the binary search algorithm. So in binary search, instead of looking at the first element, I directly move on to the centermost element of the array. Okay. So in the first step itself, I will look at the centermost element, which is 20 in our case. I compare 20 with 32 and it's not equal. Now, what sorting did to this array is that it gave us an answer that all the elements on the left of the centermost element are going to be less than 20, and all the elements to the right of the centermost element are going to be greater than 20. Okay. So now utilizing this, I can see that my key is 32, which is greater than 20. So I can reduce my search space by restricting it to only the right half of the array and discarding the left half. So in the first step, I compare to the middle element. Then in the second step, my array has reduced to 25, 32, 38. Now I'll do the same thing. Instead of starting from the beginning, I'll again go back to the centermost element, which is 32, and I'll compare this to my key, which was 32, and I'll reach the answer that okay, the element exists in the array. Now the number of steps to find the key here is just 2. Okay, so as you can see in the previous step where we're doing naively, even though the array was sorted back then also, we took 6 steps to arrive at the answer that okay, the key exists in the array. But with binary search, we utilized or we exploited the structure provided by sorting to arrive at the answer in only 2 steps. So now let's look at the time complexity here. Okay, so in my first iteration, I have n elements in the array. Okay, in the second iteration, I basically reduce this size by half by discarding 1/2 of the data by looking at the centermost element and comparing it to the key. Now let's say in the third iteration, okay, this number reduces to even further. Okay, it's further halved. Now after kth iteration, I will be left with n upon 2 is power k minus 1 elements. Now let's look at the time complexity. In worst case scenario, I'll keep on dividing the array until the array is not further dividable. So in the worst case scenario, I will reach a point where this is equal to 1. Okay. Now we have to solve for k. What would be the k? So I can simply transfer to power k minus 1 to the right hand side. I'll take a logarithm on both the sides and I will arrive at this. Now my k is nothing but log n base 2 plus 1. I can ignore the 1 because it's a constant term. So my time complexity here turns out to be log of n, which is logarithmic. In the first case, we saw the time complexity was linear. In the second case, we saw the time complexity is logarithmic. Now, if you look at the graph, this is O of n. And this is how O of log n looks. So, utilizing the structure by adding structure to the data, to the array by sorting, binary search uses a divide and conquer strategy to reduce the time complexity to log of n from O of n. Thank you. I hope you enjoyed.